Okay, so in 6.2, talking about angles of measure, and one of the things we need to talk about when we talk about angles of measure is a circle. And I'll kind of allude to why toward the end of the video, but a lot of what we're going to do with the circle is actually place these angles in the circle. So just some kind of different parts of a circle that are important. The first one is the arc. And an arc is just a segment of the circumference. Circumference. All right, so here's my circumference of my circle over here on the right, and maybe I have 2 points here. And of course, the segment joining them is the arc, right? So here's an arc. And you might be asking yourself, well, what about this distance, right? I could also connect these points on the circumference by going the long way around, and you're absolutely right, I could. Um, well, we're going to call this shorter distance the minor arc. The minor arc is the shortest distance. And the longer distance the way around would be the major arc. The major arc is the longest distance. So just kind of a note before we move on, right? Anytime I just say arc, that is going to imply, or we can assume, the minor arc. Always assume the shorter length. So another important part of this is a chord, and a chord is just a segment that joins 2 points, whoops, on the circumference. So if I have these 2 points here, I can connect them, I have a chord. And we have special types of chords, specifically if they also pass through the center of the circle. And this would be called, well, we know this is the diameter. Whoops. I actually want to put that over here. I'll write it this way. And then before I move on, of course, we just know that half of the diameter from the center to a point is the radius. And then, of course, a secant, one more word here. A secant is a straight line that intersects the circumference. Intersects the circumference. So maybe I have, oh, I don't know. I've got some kind of a line that intersects the circle, right, the circumference of the circle in 2 different places. And then I also have, if I wanted to just draw this in, I can also have a line that is tangent to the circle. Actually, let me just write secant in. And then I can have a line that is tangent to the circle, like this. And one of the things that we know is that the line tangent to the diameter is perpendicular. So just some things that might come in handy once we're starting to talk about this different parts of a circle. The other thing we want to talk about, if we start thinking about putting these angles within a circle, you're starting to talk about circles and maybe wondering why. Well, we can talk about angles in 2 forms, right? We can talk about measuring them in degrees, which is maybe what we're more familiar with, right? 90 degrees, 45 degrees. But we can also talk about radians. And radians are defined as, or 1 radian is defined as the angle required to produce an arc equal in length to the radius. So this is kind of the formal definition. The important piece is that there are 2 pi radians in a circle, or rather in an angle. Actually, let me reword this. There are 2 pi radians in 1 full revolution. That's better. Of the circle, right? In 1 complete turn through a circle, I turn through 2 pi radians. Well, we also know that there are 360 degrees when I do this, which leads us to our conversion. If I want to convert between radians and degrees, we know that there are, an angle of 2 pi radians is the same as an angle of 360 degrees. So one thing while I'm sitting here about radians is you're going to come across a couple different notations. So obviously degrees is degrees. That's not really a weird thing. You'll either see no units, you'll see rad, or you'll see this superscript C, all to mean radians. And I call this weird notation because the only one I really haven't seen that you're going to see a lot in our book is this superscript C that you might not be familiar with. So just to kind of keep an eye out, obviously degrees means degrees. You might not see a label, right? Sometimes we call radians a unitless measure. That's a discussion for another time. I just spelled measure wrong. And sometimes you'll see this superscript C. I haven't seen it until this book, but just so you're aware of it. So let's try some examples. If I'm going to convert from degrees to radians, I'm going to apply my conversion formula, right? Just like any other unit conversion, I need to cancel out my units by putting the conversion so that the units I'm interested in canceling out are on opposite sides of the fraction. So to convert from degrees to radians, I'm going to multiply in such a way that I have 2 pi over 360 degrees. Right? In this way, my degrees cancel out. I can go through and simplify this. Right, so I'm just going to use my calculator because I don't want to try to waste my time doing the mental math right now. Actually, this is one that I should really know, but just to make sure I'm doing this right. Right, so I multiply through, cancel out my degrees, and I get pi over 4. Right, my 45 times 2 is 90, divided by 360 is 1/4. I always want to leave my radians as often as I can in terms of pi whenever possible. Right, I wouldn't really say 0.25 pi or whatever 0.25 pi is. Right, it's less common to see 0.785 radians. It's more common, if possible, to say pi over 4 radians. So try to leave them in terms of pi when you can. We'll try 150. 150 degrees. Of course, I want to cancel out my degrees, so let me put that on the bottom. And again, I'm going to get not something I was expecting to get. Hold on, let me think about this. This, I believe, is 5 pi over 6. Trying to think back from my days of taking trig and having to commit a lot of these to memory. Yeah, it's 5 pi over 6. So again, I'm going to leave it in terms of pi when I can. You might notice, well, this fraction, actually let me, hold on. You might notice that this conversion rate is reducible. I could use pi to 180 if I want to. I like to use 2 pi and 360 just because I like to think in terms of the big picture with the full circle. But it is equivalent to use pi and 180 instead of 2 pi and 360. Take your pick. Well, let's do the reverse process. I want to now convert to degrees. So I want to actually, I can think about this because I'm writing in terms of pi, of putting the pi's on opposite sides so that they cancel out. So the 2 pi and 2 pi cancel out. This is going to be 120 degrees. Likewise here, I get 30 degrees. So super easy conversion. But it is really important to be able to be confident in using both degree measures, because you will see both in the book. You are not even just in the book, you will see both in math in general. This is something that our book really gets right, is the fact that you are going to see both all the time, right? Degrees tend to be more in applications, I suppose, right? I'm not going to talk about building a bridge on a pi over 4 radian angle. I'm going to talk about a 45-degree angle. Radians tend to be more important in pure mathematics, right? Once we start talking about graphing trigonometric functions and applying those, radians become much more the standard. Your calculator has both options, so be careful. Make sure your calculator or your GDC is in the appropriate mode. All right, just be careful. So moving on kind of back to dealing with circles, talking about sectors and segments. And both of these are parts of a larger whole, but a sector is the region enclosed by two radii, right? Two radiuses, radii, and an arc. So maybe if here are my radii, 1, 2. So here is my radius, sorry, my sector. And a segment is a region enclosed by a chord and an arc. So maybe here is my chord. This would be my segment. And for our intents and purposes, we're really not going to think all that much about segments. Sectors are the more important thing. A couple other things we can do here. We keep talking about arcs. Well, what's important a lot of times is the arc length, right? The length of the arc around my circle. Well, if I think about an arc, actually, let me just draw like a smaller circle that I can start to mark up, right? If I think about an arc, let me think here. How do I want to show this? If I think about an arc, yeah, that works. Here's my arc. If I think about an arc, it's a part of the whole circumference, right? This is kind of a fraction or a percentage, proportion. I'll just say portion. Why complicate it, right? This is just a portion of the circumference. So we can derive an arc length formula very much in the same way. So the length of an arc, this cursive L so it doesn't look like a 1, is some part of the circumference. Well, the circumference is 2 pi r, we know this. And how I'm going to figure out the portion of it is to actually take a portion of the 2 pi radians that the full circle encompasses, right? If my radius is only going to sweep through a certain angle, some angle theta, then I only need to consider that part of the full circle, which is where I'm using this theta over 2 pi. Obviously, you might see that this can be simplified to just r times theta, as long as theta is in radians. Right, so we're kind of thinking about the arc length as a piece of the full circumference, some percentage, so to speak, of the circumference. And how can I tell that percentage? I can tell that percentage by taking whatever percentage angle of the full circle I'm sweeping through. We can think about the area of a sector in very much the same way. So if maybe I have another sector, so maybe I'll just draw, actually we can just use the one that I just came up with here, right? If I want to use this sector here, well, this is clearly a piece of the whole pie, right? It's some kind of part or portion of the full area. Well, we know our full area is pi r squared. And once again, I'm taking some percentage of the full revolution, 2 pi, and that's my angle theta. So there's some angle theta here. So, of course, you might see again that this can be simplified to 1/2 r squared theta, and once again, theta is in radians. So actually, before I talk about prior knowledge, let's try a quick example. I want to find the arc length and the area. If my radius is 5 centimeters and I'm sweeping through an angle of pi over 3 radians. Right, so if I wanted to sketch it out, I could. Close enough. Here's my radius. Maybe here is my angle theta. So I want to know the length of the arc, and I also want to know the area of the sector. So I want to know this portion in red, and I also want to know this length in green. So let's do it. Length is just radius times the angle. So this is going to be 5 times pi over 3, which is, well, we can just leave it as 5 pi over 3 for now if we want to. And of course my area, we can calculate by doing 1/2 r squared theta. 1/2 r squared is 25, theta is pi over 3. So, and for the time being, just for the sake of time, let's just call this 25 pi over 6 centimeters squared. So it's just that simple as using the formula. But we come to kind of a crossroads here, right? There are really 2 different formulas presented each time. There's one kind of based on our prior knowledge. Let me use a completely different color. Right, we've got one that's kind of based on our prior knowledge, and one that traditionally we would maybe have to memorize. Once again, we've got one based on our prior knowledge and one that we classically have to memorize. So I'm presented with 2 different options. You don't have to memorize these formulas. And one of the things I love to tell my students in math all the time, as a lot of you guys know, is that I hate memorizing in mathematics. I hate the M word in math. Because a lot of these derivations that we make you memorize are actually pretty intuitive. So kind of combining our prior knowledge, we've learned 2 things, right? Sector area is just a portion of total area. And that portion is going to be calculated by whatever portion of the full revolution that I'm moving through. And then arc length is very much the same thing. Arc length is just a portion of circumference. So if maybe you can't find the formula in your formula booklet, maybe you just don't want to use the formula booklet for this, you think it'd be faster, I have the option, if I just talk about having options here, to just apply your prior knowledge. To say, well, I know that my arc length is based on my circumference, but it's some proportion or portion of the circumference. Well, then I can just simplify this myself, and I've derived the formula for myself. No memorization. Or if you want to, the formulas really aren't that bad, and if you want to just memorize them and say L is r theta and A is 1/2 r squared theta, you absolutely can, but your memory isn't as strong as we like to believe it is. So, whenever I can, I like to try to use my prior knowledge, but I understand that a lot of times requires a lot deeper um, kind of grasp and knowledge of the thought process. So, in a lot of cases, we do tend to memorize just because, for the time being, it's easier. But in the long run, especially preparing for a 2-year exam, if I can really be able to derive these for myself, to cut down on the memory, then a lot of times I think that's encouraged, and a lot of times I think that is more beneficial.